Hello everybody, I'm very happy to be with you in this, the third lesson of the third course of our academy, the flow of fluids in pump practice. This lesson, the title of this lesson is Bernoulli's theorem, or is this Euler's? What is the reason to use this title? First, who was Daniel Bernoulli? Daniel Bernoulli was born in Groningen in Netherlands. He published his known principle 1738 named Hydrodynamica. And regarding the first question or about the title of this lesson, he worked in St. Petersburg University together with Euler, the great mathematician. The thing is that Bernoulli wrote his principle in verse, and Euler, who was the most prolific mathematician of that century, I believe that of all the times, put his equation or wrote his principle or the principle of Bernoulli in a differential form. So the equation we know, the formula we know, was written or developed by Euler. So they together created this famous equation that is used even today, 300 years later. Let me explain first the two different views of fluid motion that are normally used. One is the Lagrange method. Lagrange also worked at the same time with Bernoulli and Euler in St. Petersburg University. It is very interesting to know that. Well, the Lagrange method, what we do here is to study the movement of a particle moving through the flow. We follow the particle movement through the flow, like that. Only one particle. This approach is not the one we will use in our case to study pumps. Normally, the approach that we use to study the fluids is the Euler's method. What we do is to fix a position in space, normally a volume, and study the particles moving through this space or through this fixed volume. So what we have is a control volume. We have fixed the volume and study what happened when particles or fluid pass through this volume. For example, if we have pipes, we define initial section 1, section 2, and we study what happened at the entrance of this volume and what happened outlet section of the volume. Real flows, everybody knows that real flows are very complex. Why? They are normally three-dimensional. To describe flows, you will need or you will require three space coordinates. Another thing, flows are unsteady. So, fluid properties at what point change with time. Another thing, the friction, viscosity produce energy loss. Another thing we have already seen before, the fluid density may be variable, especially for gases. Another point of complexity, flows are non-uniform. If we analyze a cross section of the conduct of a pipe, and we look at how behaves the velocity vector, we can see that velocity vector change across the section. So we will have the maximum velocity at the center line, for example, of the pipe, and near to the wall of the pipe, we will have zero velocity. So what we should do, the only thing is for us users of pumps to simplify flow. What simplifications are used, and what simplifications we will use to define the Bernoulli's equation? The first ones, properties change only in one direction, the direction flow. Let me say that we are focusing all these concepts to the application of user of pumps. If we want to design a pump or to provide a CFD analysis, other approach should be considered. But for our purpose, to determine the pressure losses in a pipe, to select a pump, these simplifications are completely sufficient. So, for example, we have a pipe, and properties of fluids will change only in flow direction. The flow will be uniform. Let's study this cross section, what happens with velocity. Velocity does not change across the section. The velocity module is the same at the center of the center line of the pipe than at pipe walls. What does it mean? That we will work with mean velocities, only one value of velocity. This approach we will use always for this application I'm mentioning as a pump user. The flow is incompressible. We know that liquids are almost incompressible. We can make this approach, this simplification, because the fluids pumped by pumps are liquids, so that's okay. The other one, the flow is steady, doesn't change with time. What we do is to study the movement of the fluid at each instant of time. So we will always consider that the flow is steady for our application, I insist. And the last one is applicable only to this case we are dealing with today, that the flow is ideal, is non-viscous, is frictionless. So there are no effects of viscosity, no pressure losses. It is an ideal flow. In practice, we will always have pressure losses. So from this, we will apply, I insist, these 5 approaches or these five simplifications to the study of this equation. So for a one-dimensional, uniform, incompressible, steady, frictionless flow, the sum of the pressure energy, the kinetic energy, and the energy due to geodetic height is constant. Let's see how is the form of the Bernoulli's equation, integrated Bernoulli's equation. Let me remember that Euler wrote the differential equation to describe this theory. He defined the Bernoulli's equation to a straight line. We, from a practical point of view, will apply all these assumptions I mentioned before. We'll apply this equation, and we will see this equation integrated and with the mean values I mentioned before in every section of the control volume. So we have this conduit. We select this control volume between the section, the entrance section and the 1, and the outlet section 2. Let's establish these reference planes, and the center line of this conduit is elevated a height Z1 from the reference plane and Z2 for the section. So what it reflected in this equation is the sum of the energy pressure. Remember that we have seen already in lesson 2 that the static pressure expressed pressure unit was a form of energy density, pressure per unit of volume. So the sum of the static pressure plus pressure due to the height Z plus kinetic is constant in every section. There are no pressure losses, as we have predefined. This equation, although ideal, will be the starting point to define the equation of energy, and we will see later how to add to this equation some terms that will be needed to add for real flow, especially with pumps, terms such as the pressure or the pump head, the pressure losser, etc. Well, I'll be waiting for you in the next lesson, so bye bye.